Have you ever stopped to think about what it takes to build a tunnel? Not just any tunnel, but one deep inside the earth, carving out arteries of solid rock to get to precious minerals. Well, today, we're going to dive into this incredible feat of engineering, where we literally build the world right under our feet. So that's the big question, isn't it? How do you pull it off? It's a massive puzzle that involves geology, physics, and, yeah, some of the most powerful machines you've ever seen. We're going to break down the entire process for you, from a simple patch of empty land to a fully functioning underground lifeline. And when I say powerful machinery, I am not kidding. Just look at this thing. This is a tunnel boring machine, or TBM for short. It's pretty much a moving factory that doesn't just dig, it grinds its way through solid rock nonstop. But here's the thing, as incredible as this is, it's just one piece of a much, much bigger story. Before you can even dream of flipping the switch on a beast like this, the real work has to start. And that brings us to our first phase, which I like to call seeing in the dark. This is all about prospecting and exploration. Because the first rule of tunneling is actually pretty simple. You can't dig what you can't see. So before anyone even thinks about moving a single shovel of dirt, you have to create a super detailed picture of exactly what's down there. What's really wild is the sheer scale of this search. Engineers use this concept of going from whole to part. So they might start with a huge region, maybe thousands of square kilometers, and then just methodically narrow it down through these 4 phases. They get more and more detailed until, finally, they've pinpointed the exact spot. So how do they actually see underground? Well, they have a whole toolkit of tricks. You can think of it like giving the Earth a full medical checkup. They use geophysical surveys, which are kind of like a CT scan, and they analyze things like stream sediments. But for the ultimate proof, they do what's called core drilling. This is like taking a biopsy, where they pull out actual cylinders of rock from deep underground to see exactly what they're dealing with. Okay, so once they have all that incredible data, it is time for phase 2, drawing the map. This is the part where all that science gets turned into a real, actual blueprint. It's about taking all that raw information about the rocks and turning it into a safe and practical engineering plan. And this right here shows you just how complicated that is. It is not a straight line from A to B. It's more like a constant feedback loop. You've got info about the geology feeding into computer models, which helps with the design. But then, things like what kind of equipment you have, or safety regulations, they feed right back into the process. It's a constant dance of refining the plan. So here's the key takeaway. All of this data, how strong the rock is, where the groundwater is, even the natural stress in the earth, it all gets pulled together into something called a geotechnical model. This is basically the ultimate digital 3D map of the underground world, and it's going to guide every single decision they make from here on out. All right, all that careful planning has led us right here to the heart of the action, phase 3, the advance. This is where we finally start breaking some rock. It's all about a powerful, repetitive cycle that pushes that tunnel forward 1 meter at a time. And for a lot of tunnels, this 4-step process is the fundamental rhythm. It's the very heartbeat of the project. It's this carefully choreographed dance. You drill very precise holes, load them up with explosives, blast the rock into manageable pieces, load up all the debris, a process they call mucking, and then haul it all away. And then you do it all over again. But you know, setting off explosions isn't the only way to do it. There are really 2 main approaches. You've got the classic drill and blast method, which is super versatile and great if the rock conditions are tricky or keep changing. And then you have mechanical excavation, using those giant TBMs we saw. TBMs are amazing for their continuous speed, but they work best when the geology is pretty straightforward. And this quote just perfectly captures the raw power of a TBM. See, it's not about just chipping away at the rock. No way. It's about applying this immense, focused pressure with these rotating steel discs that literally fracture and shatter the rock face right in front of it. It's just a relentless, grinding advance. Okay, so we've made a hole. Great. But you've just created an empty space where millions of tons of solid rock used to be. And guess what? The Earth naturally wants to squeeze that hole shut. So this brings us to the final and maybe most critical challenge, phase 4, taming the Earth. How in the world do you keep the tunnel from collapsing? The key concept here is something called rock reinforcement. Now, this is way different from just propping the tunnel up from the inside like in an old movie. Reinforcement means you install things into the rock itself to help the rock support itself. The analogy of giving the rock stitches is honestly perfect. You're making the surrounding rock stronger from the inside out. And the undisputed champion of reinforcement is the humble rock bolt. It looks so simple, but it is an incredibly clever piece of engineering. A rock bolt can act like a suspension hook, hanging a weak section of rock from a stronger layer above it. Or it can clamp a bunch of thin, weak layers of rock together so they act like one single super strong beam. Or it can just pin one unstable block of rock in place so it can't fall. So smart. Now, to help out the rock bolts, engineers often use a technique called shotcreting. It is exactly what it sounds like. They literally spray a layer of concrete onto the tunnel walls, and it acts like a protective skin. It seals up the newly exposed rock, stops little bits from flaking off, and protects it from weathering over the years. So there you have it. We've gone from surveying the land, to drawing the map, to drilling and blasting, and finally to securing the tunnel for the long haul. And with that, the lifeline is officially open. Because remember, the tunnel itself isn't the end goal. It's the pathway that makes everything else possible. And the scale of all this work is just staggering. To give you some perspective, just one pioneering company in this field has bored over 3,500 kilometers of tunnels all over the world. That's almost the distance from New York to Los Angeles. All of it built deep underground. It's mind-boggling. And that's why this is so important. These tunnels are the invisible lifelines of our entire modern society. They give us access to the essential resources that build our homes, power our cities, and create the technology we use every single day. We have gotten incredibly good at this whole process, but the journey is definitely not over. As we keep pushing the boundaries, needing to go deeper and deeper into the earth, into harsher and more complex environments, you've got to wonder, what's next? What kind of new innovations will we need? What will the tunnels of tomorrow even look like? That's something to think about.